Okay, so the end of this section talks about equilibrium and metabolism and what that means for us. So something at equilibrium is when it's going both ways at the same amount of time. So if you think back to chemistry, a reaction at equilibrium is the same amount is going forward as is going backward. And diffusion at equilibrium, same amount of molecules are going this way as are going this way. Means it's steady, it's stable, it's very stable. And so reactions that are in a closed system, meaning that they're not interacting with the universe at all, eventually reach equilibrium and then do no work. So in reality, there aren't really any closed systems. Things are always interacting with the universe. But we can talk about these things as closed systems just as an example to like hypothesize about what things might be like if we weren't interacting with them. And so when we talk about closed systems, it's just a hypothetical. Okay, so there's nothing really that's like that. But eventually, if you're not putting in any energy, if something's reversible, meaning it can go both ways, it will eventually reach equilibrium. And then nothing's going to happen. No work is going to get done because it's the same forward and backward. They would just cancel each other out. But cells are not at equilibrium, like I said, nothing in the real world is. They're open systems experiencing a constant flow of materials. So we constantly need things inward. We're making waste. So we're constantly putting products and waste outward. So we're not at equilibrium or even close to it. And a defining feature of life, like it says, is that metabolism is never at equilibrium. So if we were at equilibrium, then we could do no work and we couldn't power our cells, we couldn't power our muscles. Life wouldn't happen because we need that energy for processes to happen. So life is never, ever, ever going to be at equilibrium. Metabolism would never be. And then it says a catabolic pathway in a cell releases free energy in a series of reactions. So remember that catabolic is breaking down larger, more ordered molecules, less stable molecules, into smaller, less ordered, more stable molecules. So that's like glucose. We have glucose, it's a larger molecule, it's far more ordered, but far less stable than carbon dioxide and water. So as we break down from glucose to carbon dioxide and water, we increase stability, but decrease order, and we're releasing energy. And then what that says that I'm covering is that closed and open hydroelectric systems can act as analogies. So here is a closed system. So it's isolated. It's not interacting with its surroundings in theory. And so water is moving this way, right? So we're losing free energy. Here we have a lot of free energy in this system, a lot of power to do work, so we're turning this wheel because the water's moving, so that's where the work is going, our free energy. We're powering the wheel, the water's moving. As we get down here, we're at equilibrium. Water can move both ways. Free energy is zero, the wheel's not moving. So that is a system at equilibrium. It has no power to do work, no power to turn that wheel. But if the system's open, then it can keep doing work. So if we keep putting in water and water can leave out the bottom, then this wheel is forever going to turn because delta G is always going to be less than zero. We're always going to be losing free energy. So there's a lot of free energy right here, not a lot of free energy right here. So we're losing free energy and it's always going to be doing work. That wheel's always going to turn if it's open and we can put in water and lose water out of the side. This is a great analogy for our cells because remember that metabolism is like a roadmap. It's not like a one straight path, and it's not A becomes B. It's A becomes B, becomes C, becomes D, becomes E, and we finally want E at the end. So each of the products in the middle is actually a reactant for another one in a metabolic pathway. So that's kind of like what it's like here. So we're putting in a reactant, it becomes a product. That product becomes a reactant for another reaction, and then it becomes a product. But again, it's a reactant for another product. So we're always pulling products away, making them reactants, so we can never accumulate products because they're always turning into something else. So the water right here never reaches equilibrium because we're taking it away to become something else. So that's why we are always having a delta G less than zero. We're always losing free energy. We have so much more free energy than right here. And right here we have more free energy than right here. And right here we have more free energy than right here. So we're always losing free energy and we always have the power to do work. And that's the end.